Hi, I'm Marilyn Klein, President and owner of Fiberglass Developments.
Hi, I'm Scott Campbell, Sales and Operations Manager at Fiberglass Developments.
In the spring of 1994, I was contacted by the Premix Corporation to assist the University of Akron in building an all-composite super mileage race car. Although we typically are not fabricators, I agreed to provide a fabrication leader in exchange for being able to videotape the entire process of building the car. Premix, Goodyear, and Fiberglass Developments all participated in financial support of the car and are proud to have been part of this unique educational project. The essence of the super mileage competition is a race among vehicles all obtaining in excess of 1,000 miles per gallon of fuel. Our goal was to assist the students and faculty in building a light and efficient composite car to compete in this race.
I was the fabrication leader and guided the team of engineering students through the process of design, construction, and fabrication of their composite car.
The process of building the plug through completing the finished shell took about 6 months and is edited into 2 videos. This is the first video, and here we demonstrate the steps of building a large plug and the advanced mold making techniques required for full-scale applications. The second video in this series demonstrates vacuum bagging techniques and the sandwich core construction used to build the graphite honeycomb shell. The University of Akron College of Polymer Science requested that we assist the College of Mechanical Engineering in building the composite shell. The mechanical engineering students would then be responsible for adding the engine, steering, and all of the other components of the car. We thank the University of Akron Visual Services Department for shooting all of the in-process footage that you see in these videos.
The car that we built was intended to be an evolution of an existing metal framed car. Our goal was to eliminate the metal frame and create a vehicle which was lightweight yet strong enough without the frame to support all the loads of the car. This included all the systems as well as the driver. As I began the project, I knew in my mind's eye what the finished car would look like. I knew that the shape of the new car would have to be rounder and more uniform on the outside surface than the old car. It would also have to be slightly taller and wider because we needed to use 27-inch bicycle wheels instead of the 20-inch wheels used previously. The cockpit needed 3 feet of legroom for the driver as well as a windscreen which provided 180 degrees of vision from right to left. As a result, the shell of the car would have this basic shape. We needed to create a model which had the exact shape of the finished car. This model is called the plug. From the plug, we would pull 2 female molds. These molds would then be used to make a top and bottom shell for the car. As we begin construction of the plug, you'll want to keep in mind that we are following the same outline as demonstrated in our video, The 7 Steps of Molding Fiberglass. If you are new to molding and need a more concise explanation of the process, you might wish to review that video. This video and its sister do assume that the viewer is at an advanced level in hand laminating composites.
The first step of mold making is developing the plug. In many cases, such as this one, there is no existing shape available to use as the plug, and it will have to be created from scratch. Before we begin construction, however, there are 3 rules to remember in all plug construction. First, the plug must be geometrically identical to your desired finished part. Second, the surface of your plug must be absolutely perfect. There can be no flaws, pinholes, or dull spots, as these will transfer directly to your mold and then to your parts. Third and finally, the plug form needs to be strong enough to support the molding materials before they cure and not distort during construction. Remember, the key to successful molding is to create a perfect plug. It doesn't matter what type of materials are used or how inexpensively the plug is made, but it must meet these 3 criteria.
A plug as large as the one demonstrated in this video might be archived so that if additional molds were necessary, the master plug would always be available. If you know that the plug will be saved for future use, build it even sturdier so it will survive multiple vigorous mold releases. When a plug needs to be created entirely from scratch, the first step is to lay out your design. Design engineering with composites is beyond the scope of this video, but I will outline some helpful hints based on my experience throughout the process. The car had to meet the basic parameters stated above in the introduction. Provisions were also made for steering and braking systems, the driveline, axles, motor mounts, and safety systems. When construction began, many of these accessory systems had not yet been engineered, so I had to design a platform that left the students as many options as possible. These types of requirements affect the size and shape of the plug, but there are additional considerations as well. You must anticipate your molding process. In this case, we need the car to have a smooth outer shape while using sandwich cores inside to add stiffness. To achieve this, we had to construct 2 open female molds. Ultimately, the molds need to be released from this plug, so you must plan to divide the plug at a point which does not create any negative angles. A negative angle occurs when an area below your mold seam is wider than the area at the parting line. You have to anticipate this when you design your plug and make sure that no negative angles exist. Do not count on the molds flexing enough to release around a negative angle. They will not. If negative angles are unavoidable, the mold will have to be constructed in several more sections. The second thing to anticipate is the ultimate layup of parts. Trapped air in the mold or in the parts results from either inadequate saturation or resin and reinforcement pulling away from surfaces that they can barely reach. You want to avoid right angles and tight corners in your design where air pockets can form. As you can see from this later shot of the rear of the plug, I tapered the curves as much as possible to avoid this. Finally, the vacuum bagging lamination method used to construct the final parts also meant that a wider than average parting flange be incorporated into the molds as the point of attachment for the vacuum bag. This required only minor modification to the existing part of the mold. After you have completed your design, you're ready to start building the plug.
The second step of plug making is to build a sturdy frame. The size of the Akron vehicle made carving the plug from one solid block of material impractical, so a framework was constructed to provide the basic 3-dimensional shape. Full-scale, cross-sectional views were cut out of drafting paper and glued to plywood sheets. These cross-sections were the bulkheads, which made up the exact outer surface of the plug. To orient and support them properly, slots were cut in both the bulkheads and in longer framing boards. This allowed the bulkheads to rest in the frame precisely located along the axis of the car. The plywood is the first outline of the plug. Earlier, centered holes were drilled 20 inches from the base of each piece of plywood. These holes accept a large dowel rod which supports the tops of the bulkheads and helps them to remain in position. After gluing the plywood and the frame together, the rod was inserted. Notice that the framework is all internal and will not affect the surface of the plug. You must make sure everything is straight. Use a T-square to verify the positions before continuing. When the glue dries, the bulkheads will be securely fixed in place.
The third step of plug construction is to make the surface for the frame. We had decided to make the plug solid. Just surfacing the bulkheads wasn't practical. Filling the plug with expanding polyurethane foam is ideal. Once cured, it is easily cut and carved. It is relatively inexpensive and will expand to fill even oddly shaped cavities. To save on foam, we didn't fill the entire plug, just the surface perimeter. It was easy to tape newspaper to the bottom of the frame, creating loaf pan type cavities when the frame was flipped over. Pouring into these square cavities was straightforward, so we began there. You have to seal all the edges with tape to prevent the foam from draining out. The foam is a liquid which you pour into the cavity. It will expand to 30 times its volume in the liquid state. If the size of the cavity is known, divide that by 30 to determine the volume of foam to mix. More often, the size is unknown, so pour just enough to cover the bottom uniformly until you gain experience with how the foam expands. We continued mixing and pouring until the bottom of the frame was filled. As you can see, some sections were filled in multiple pours, while others rose properly the first time. All of them will be trimmed later to a uniform height. After the bottom was filled, we tipped the frame on its side and taped in newspaper like we did on the bottom. However, this merely created broad and shallow cavities which followed the outer contour of the car. We soon found that these types of cavities do not contain the foam well enough, so we did not construct any more. We were able to finish the side this way by making multiple pours, but it was neither quick nor clean. We discovered a better way. We filled the inside with newspaper and stuff to create the inner pocket. And all we're doing now is coming along and loosely applying newspaper, loose enough so that it can expand and have the foam come out beyond it so we can cut it off later and shape it. The opposite side and the rest of the frame were filled from above using this technique.
At this point, the surface is quite rough. You want to make sure that you have overfilled and have enough to trim. Adding or filling starts becoming more difficult from this point forward. The newspaper on the outside will simply be shaved off with the excess foam. Now you will begin the fourth step of building your plug, which is carving it to the correct shape. Saws and knives easily cut the foam, but it cannot be hot wired. You want to trim away the excess and sand the surface smooth. Remember that the plywood bulkheads provide the actual finished dimensions, so do not gouge the foam deeper than the plywood. Trim as much as possible with the saws before trying to sand. Scott used an electric belt sander to quickly trim the excess foam and newspaper which the saws did not remove from the frame. The belt sander was fast, but in some areas he removed too much material. Try to keep your cutting surface on the bulkheads, or you cannot gouge the foam. A straight 2x4 about 4 feet long with sandpaper glued to the surface makes a great sanding block for the larger and flatter sections. Also, polyurethane foam is easily sanded using another block of itself. This works particularly well in areas of detail. Before long, you can see that the plug is taking shape nicely. Most of the newspaper has been removed and the foam has closed the gaps between the bulkheads. 2 days later, the entire plug has been filled in and shaped. Even to the casual observer, it is beginning to resemble the planned shape. In some areas, the foam was shaved too low, and in others, air pockets were trapped. These can be filled with a standard auto body filler, or you can mix phenolic microballoons with your molding resin to create a spreadable, sandable paste filler. We had body filler on hand, so it was used on the areas we needed to reconstruct. The surface does not have to be perfect, but it should not be higher than the surrounding foam. Once all the high spots on the foam were removed, the plug was skinned. This is the fifth step of building the plug.
The surface has to be completely non-porous and pretty resilient. Typically, it is fiberglass. This mat layer serves two functions. First, it protects the foam from accidental crushing during handling. Second, and more importantly, it provides a solid base for all other surfacing compounds to be applied later. Thoroughly saturate pieces of fiberglass mat, then lay them in place. Begin with torn chunks, which approximate the space between the bulkheads you are going to fill. It may be helpful to paint some resin over the foam before applying it in order to fill many of the tiny holes. The foam holds quite a bit of air because the cells were cut open during the shaping process. Try to work out the larger air pockets by stippling with a brush or wiping with your gloved fingers. A groove saturation roller also helps to remove the air. Mix batches of resin in quantities which can be applied before the cure sets in. Begin with small pots until you become familiar with the cure cycle. I continue to work from batch to batch and am not concerned with how much of the fiberglass has been cured. As I go along, I make sure that each piece is laid properly without trapping air. That way, if the resin does set up, I don't worry about poor adhesion problems. One even coat of fiberglass is all that is needed to coat the plug for protection. If necessary, extra layers may be added to fill minor low spots. Work consistently to cover all exposed foam. The body filler can be covered just like the foam. I worked alternately between filling, shaping, and skinning the foam until the entire framework was uniform. When the entire framework has been skinned, it needed to be lightly sanded to remove any stray fibers and promote good adhesion for other surfacing compounds. This is also a good time to look for air pockets which need to be ground out and repaired. The portions of mat which were ground out over the air pockets are being replaced. Other areas are being filled because too much foam was removed during the trimming stage. Notice that the mat saturates quicker when placed on a non-porous surface than it did over the foam. It is possible to work faster now, but still watch out for air bubbles. I mentioned it earlier, but this is a demonstration of a groove saturation roller at work. It has no equal for quickly and thoroughly removing air from a chopped mat surface.
Look carefully for areas where the fiberglass did not stick to the foam. These areas will feel spongy when pressed and must be cut away. It is now time to proceed to the sixth step of plug construction. The sixth step of plug making is to complete the final shaping.
In the areas where the fiberglass skin has correctly assumed the shape of the vehicle, it can simply be sanded with 80 grit dry sandpaper to prepare it for priming. In our case, the plug needed quite a bit of final shaping to achieve the desired contours. The bottom of the plug was closest to being correct, so we started there. We added material to the bottom to level it, and to the sides to smooth the transition with the bottom. Use some type of sight gauge to determine where the material needs to be added or removed. Here I use a straight edge to look for low spots.
Two circumstances existed at this stage which caused us to adjust the normal sequence of operations during the final plug shaping and mold construction. The first circumstance was the current shape of the plug. Although the framework had been designed with no negative angles, it had very little taper or draft to its sides. It was decided that the lower carbon body shell would be extremely rigid and in its present form difficult to release from the mold. Consequently, the mold sides needed a greater taper. The ideal place to anticipate this would have been during the design of the plug. However, this is the final stage to make any changes, and it is better to correct it now than to have the part stick in the mold or be damaged trying to force its release.
Following this line, I built a taper to a height of 3/8 of an inch over a 14-inch span per side using glass reinforced body filler. However, it had to be blended evenly from the bottom of the plug to the parting line and added another week to the project. The desired result was achieved though, and the material added 1.5 degrees of draft to each side of the plug.
The second circumstance which affected the final shaping of the plug was the timetable of the project. The sooner the students could receive the structural or bottom portion of the vehicle, the earlier they could begin final assembly and testing of the engine and other critical systems. In an attempt to compress the schedule and produce the lower shell earlier, only the bottom of the plug was fully shaped and surfaced before the lower mold was made. We then came back and surfaced the top of the plug. However, to teach these mold making techniques in the proper sequence, we will discuss finishing the plug in its entirety. When that is complete, we will proceed to mold construction.
As stated earlier, the bottom of the plug was finished first. We pick up now forming the top of the plug. To speed the shaping, I switched to a quick-setting drywall compound to rapidly blend the top into the bottom. This material dries in 20 minutes without cracking and sands easily. I'm using a fairly wide applicator where the sides are flat enough to allow it. This saves on sanding later. My shaping tools consist simply of 2 drywall sanding blocks of different lengths and many drywall sanding screens. Since the drywall compound is softer than the body filler I used on the lower portion of the plug, I am able to sand right next to the finished lower surface without changing its shape. This transition area is the parting plane which divides the 2 molds, and it cannot be altered. I am now sanding one of the last layers of drywall compound. I use a crosshatch pattern, a longer stroke, and a longer sanding block to make sure the flatter areas stay true. The switch to drywall compound probably saved a week's worth of work grinding on the body filler. I used a flexible drafting tool to check and recheck my contours from side to side. Cardboard templates could also be used, but I found this to be quick and accurate enough. Check every 6 to 12 inches depending on the length of the sanding block being used. I finished covering the plug with regular drywall compound to get the smooth finish and sanded it with 180 grit dry sandpaper. At this point, I blew the remaining dust off the car before checking all the measurements again. I knew that the shape that had been developed would be the final design of the vehicle.
After the plug achieves the proper shape, it must be covered with a material which can be sanded and polished to a high gloss finish. This is the final step of building the plug.
The drywall compound was sealed with a latex primer available at most hardware stores. This was sprayed on, then lightly sanded with 240 grit dry sandpaper. The product I am spraying now is an automotive epoxy primer which I use to seal the entire plug surface. This epoxy sprays on easily, is extremely durable, and can be polished to a mirror finish. I first applied a light tack coat and let it dry. Then, we filled any visible pinholes with a very light spackling compound. We got this at the hardware store as well. It is easy to apply with your fingers, and the excess is removed with the palm of your hand. Next, I sprayed on a medium coat of epoxy primer to cover the spackling compound. This only sat long enough to tack up. I applied a final coat of epoxy primer to seal everything. The primer must be thick enough that later sanding operations will not cut through it. The plug sat for over 24 hours to be sure the epoxy had time to fully cure before sanding would begin. The sealed plug needs only sanding, polishing, and waxing to be ready for mold construction. While the surface may appear fine, a closer inspection usually reveals a slight orange peel texture. This texture, along with any other minor flaws, must be sanded off the plug or it will be transferred to the mold surface. Begin using 240 grit wet sandpaper and a wet or dry sanding pad. Clean the paper frequently with water to remove dust and to lubricate the plug's surface. Rinse the entire surface with clean water, dry, and inspect. Do not proceed to the next grade of paper until all the orange peel texture has been removed. When only 240 grit scratches remain, move on to the 320 wet paper to remove them. Use consecutively finer grades of paper until the scratches are very fine. We stopped after using 600 grit paper and washed the plug again. The plug now has uniform fine scratches over the whole surface and is ready for buffing. Next, we spread machine glaze over it. With clean terry wipes, we hand buffed the surface because a machine polisher was not available. I personally recommend renting a machine polisher. Not only does it make the job easier, it polishes to a higher luster as well. Number 11 parting wax was then applied to the plug, allowed to haze, and buffed off. A total of 6 coats of wax were applied, allowing the wax to harden for an hour between every 2 coats.
The resulting waxed plug is now ready for the upper mold to be constructed. This shape is exactly what the final vehicle will look like. It has a very high-quality surface finish, free of scratches, and is bonded securely to the supporting layers below. The plug is now complete. It is identical to the desired shape of the finished car in every detail. We are now ready to identify the parting plane and build the separation flange. It is this line which will separate the top from the bottom mold half. As we explained when finishing the plug, we had to construct the bottom mold as soon as the bottom of the plug was finished. As a result, this step of constructing the parting flange was performed when the plug was only partially finished.
Due to the size and the taper toward the nose of the vehicle, a full-size parting board was not constructed as it was in our molding fiberglass video. It was still necessary to create a flange which would follow the parting line and separate the mold halves. 14 inches from the bottom of the plug was a crest or waist, which was the widest portion of the model. This was the parting plane which would divide the plug into the upper and lower mold halves. Please note that the plug is resting upside down awaiting molding. Also note the wax Formica board screwed to the back, forming the flange at the rear of the mold. Using modeling clay, we constructed a 3-inch deep shelf around the entire perimeter of the plug. I used a razor blade to smooth the clay, making sure that I didn't hit the surface of the plug. The shelf was supported with more clay and cantilever triangle supports made of sheet metal. The shelf needed the triangles to support the weight of the molding materials used to construct the flange. Since the plug was already waxed, it was ready for PVA. The clay shelf and the entire exposed half of the plug were then sprayed with PVA. 3 light coats were applied to the highly waxed surface and allowed to dry. The mold surface should appear uniform and dry before continuing to molding. At this time, the lower mold was constructed off camera and removed from the plug. Later in this video, we will document the construction of the top mold in detail. While the bottom mold was off the plug, our next step was to extend the flange. We'll take a moment to explain why this was necessary. During the vacuum bagging process, the bag would actually be attached to the flange. Although 3 inches might have worked, a narrow flange makes it difficult to attach all the other vacuum bagging materials and the sealant tape. Since the mold had to be released anyway, we made the modification now so that the upper mold could be made with the wider flange already in place. You can see that the finished mold is about 5/8 to 3/4 of an inch thick. Fiberglass this thick takes time to trim even with the proper tools. To begin the modification, the flange was neatly trimmed using an air cutoff wheel. Notice that I'm wearing long sleeves and a respirator. Heavy fiberglass dust like this is best kept off the body and out of the lungs. Next, the mold was inverted on a waxed Formica board where 5-inch wide strips of chopped strand mat were butted against the existing flange. These were added until they matched the height of the original. Then, wider portions of mat were overlapped onto the mold and the flange. When the flange matched the thickness of the rest of the mold and was continuous around the full perimeter, it was allowed to cure, and then it was released from the Formica. Once again, I used an air cutoff wheel and trimmed the excess from the edges of the widened flange. The surface of the new flange was very good. I still needed to use the belt sander to level the transition between the old flange and the new one. I wanted to mold the flange on the upper mold as smoothly as possible. Also, a smooth flange helps to reduce leaks during vacuum bagging. Except for hand sanding with finer paper and blowing away the excess dust, the lower mold was complete and ready for molding the top half. I waxed the bottom mold again before replacing it on the plug. This was in case any resin dripped into it while I was constructing the top mold. We had already removed all the clay residue from the plug and the waxed flange.
With the bottom half of the mold returned to the plug, we are ready to document construction of the top mold half. The entire surface of the plug was thoroughly sprayed with 3 coats of PVA before being placed back into the lower mold. Clay has been added to the new extended flange to make it even smoother, and the flange was waxed 6 times to ensure an easy mold release. More PVA was applied after the 2 were assembled so that the modified flange and exposed plug were completely coated. It will now be easy to duplicate the width of that flange into the top mold. This will be a polyester mold. A polyester mold can be used to pull polyester parts or epoxy parts, as we will do. Polyester molds are typically preferred in most large applications for 2 reasons. First, polyester resin is considerably less expensive than epoxy resin. And second, polyester construction allows the use of chopped strand mats. Most grades of chopped strand mat cannot be used with epoxy resin.
The first layer applied to the plug was the surface coat. This surface coat will create the surface of the mold from which all future parts will be pulled and is extremely critical. The quality of this layer is dependent upon the quality of the plug surface as well as the proper selection, catalyzation, and application of the gel coat used for the surface coat. We use the number 78 tooling gel coat. A good tooling grade gel coat is highly recommended for polyester mold surfaces. Tooling gel coat offers ongoing resistance to part release and has a minimum distortion. We filled several cups which could be catalyzed when they were needed.
Scott measured the MEKP using an MEKP dispenser. This ensures a proper amount of catalyst is used for the gel coat. He mixed carefully to avoid creating hot spots in the gel coat. Using a 2-inch brush, he cut in the flange area with gel coat.
It is easier to begin by brushing than spraying in an area like this. You need to cover that right angle where the flange meets the plug and make sure that the gel coat is applied evenly. Spraying directly into an area like this often results in runs or heavy sags. I'll come back and spray over it to level any brush marks, but I find this much more controlled. After the flange was covered, I was ready to spray gel coat over the entire surface of the mold.
Using the gel coat cup gun, the remainder of the coat was sprayed on. The brush strokes quickly disappeared when covered with the atomized gel coat. Gel coat is sprayed rather than brushed whenever possible. Even an experienced person will have occasional trouble with gel coat. Gel coat problems are usually a result of spraying too thick. Several thin passes are recommended.
Yeah, that's at 9 mils. That's just about right.
I waited only long enough to catalyze another quart of gel coat before spraying it over the first. Notice how I use the cup gun. It is truly a gravity feed gun, and the gel coat will run out the nozzle if it is tipped down. When it is extremely full, I keep the nozzle pointed upward until I have pulled the trigger and material begins to flow. Also, I do not release the trigger at the end of each pass like I would with a siphon-type spray system. Instead, I move quickly and watch that I don't overlap the previous pass too much.
A gel coat thickness gauge is used to measure the thickness. He checks in several places to make sure that there will be no thick or hot spots.
It's like 14.
It took a 3rd quart to build the gel coat up to the desired 20 to 21 mils. The entire gel coat layer was allowed to cure until it passed the brush test. The gel coat may sit on the surface for no more than a few hours before proceeding. You need to wait until the gel coat passes the brush test, which is when it is cured enough to not move when brushed lightly with a dry brush. After it passes the brush test, however, you want to begin laying up your mold within 2 to 4 hours to avoid distortion and blistering problems, which you would not be able to see.
If I have gel coat that has been left on a surface for more than 4 to 6 hours, I'll pick it off and start over. You really want a flawless mold, and if your gel coat is damaged, it's really difficult to repair. Next, we started reinforcing the mold. The schedule we followed was to apply 2 layers of mat followed by 1 layer of 10-ounce cloth. Then we repeated the process 4 times until a total of 12 layers had been applied. We used polyester laminating resin. The first layer of reinforcement is also very important. It must be applied without trapping any air pockets. If an air bubble exists in this layer, the gel coat is unsupported and will collapse when the mold is put into service. As a rule, neither mat nor woven fabric can be expected to lay around a 90-degree or smaller angle without developing air pockets. To eliminate air pockets in the corner where the flange meets the plug, we pre-cut strips of mat in 2 sizes. We cut 6-inch wide strips of mat which match the width of the exposed flange. These strips can be laid into place easily and have nice cut edges on both sides. Thoroughly saturate the strip of mat you intend to lay on the flange. We don't particularly care about the weight of the mold and are fairly generous with the resin content. Butt one cut edge up against the plug and the other falls evenly and minimizes the trimming necessary when finishing the flange. Watch for clear air bubbles in the resin and work them out using the brush and your fingers as you work. If you wish, paint some resin down on the flange before you lay your mat strip into place. We also cut a number of strips of mat about 8 inches wide. These I tore in half, which left 2 strips with a single cut edge and 1 frayed edge. I placed the frayed edge strips onto the plug surface by butting the cut edge into the corner against the flange. The frayed edge drapes evenly onto the plug surface where the other layers may be applied over it without trapping air pockets. This butt joint at the corners effectively eliminates air bubbles. As always, I applied these strips 1 layer at a time, watching closely not to trap air. After a few layers have been applied in this way, I place the cut edge of the strip even with the edge of the flange and allow the frayed edge to overlap onto the plug. After the flange and plug corner were covered with 1 even layer, we were ready to lay up the surface over the plug. It is easier to work torn chunks over the contours than full lengths of mat. You will again lay resin on the surface and saturate the mat as well. Applying the mat directly with gloved hands is the most common approach and allows for the feel of the plug. Stippling with a brush and a groove saturation roller help to eliminate air. You will want to apply a total of 2 mat layers to the plug and the flange before continuing with the 10-ounce fabric.
Another secret too is you don't have to work on the stuff all the time. If you get enough resin on it, okay, and you leave it sitting evenly along the top, in time it'll soak in. Like you could go to the next piece a little bit, you know. That's not what you do toward the end when the resin is hardening. But you can just kind of let it sit. And in time, just by itself, it'll soak in a little bit for you.
You need to let each of these first 2 mat layers cure individually before laying up the first layer of 10-ounce fabric. This ensures that the mold does not get too hot and distort the tooling gel coat during the cure cycle. Once these 3 layers have been applied in this fashion and the mold allowed to cool, 2 to 3 layers may be applied at a time and the mold will resist heat distortion. Continue by laying in the 10-ounce fabric between every 2 layers of chopped strand mat. The fabric is stronger and more stable than the mat and will help the overall strength of the mold. You don't want to cut the 10-ounce fabric more than necessary. It will be necessary to cut slits and some contours, but you don't want to cut strips. The properties of the fabric are best achieved by leaving it in as big of pieces as possible.
You can still apply resin liberally as needed to the plug and to the layers of reinforcement. Try to work evenly, applying the same number of layers to all areas. On large molds, it is easy to lose track of how many layers have been applied and where. If you leave a surface cure for more than 24 hours, it may be necessary to sand it prior to laying on additional layers.
After all of the reinforcement layers were applied, the completed mold half was about 5/8 of an inch thick. We usually recommend that the mold be 3 to 4 times thicker than the parts to be produced in them. This is easily the case with the top mold, as only 3 layers of carbon fiber will be used to make the upper shell. The lower mold is also plenty thick because the sandwich laminate is really only 7 layers of carbon fiber. All 7 are only 1/8 of an inch thick in areas with no honeycomb. A better gauge is to determine how long the mold is to be in service. If it is expected to be used often, make it a little heavier now so it will last.
The 4th step of molding is releasing the mold from the plug. Releasing the molds from the plug can often be a tedious process. Locate the largest gaps between the 2 molds and begin working the wedges into these locations. choose a wedge which matches the gap as they come in multiple sizes. The first few wedges are generally the most difficult to insert. Once a few are in place, creating more gaps, larger wedges may be worked around the mold until it releases completely. Never use any metal objects to aid in the release of the molds. Invariably, metal will gouge or crack the new mold. In this case, it was just a matter of inserting enough wedges around the perimeter until the mold broke free. The rear came up first, then the rest of the mold was lifted off the plug. The plug is still resting in the lower mold, but it obviously came through the molding process intact. It took many hands to lift the large waxed plug out of the lower mold. However, the two came apart easily because they had been released once before. We inspected the molds following their release. Both were found to have highly polished surface finishes. There were no marks or scratches requiring coarse sanding to eliminate, but a slight surface texture was present. The top mold looked great and the team was feeling excited. Overall, I was extremely pleased and felt that we were well on our way to making the shell.
Off camera, Scott used an air-powered die grinder just as before to trim the excess material from the flange of the top mold. After that, he wet sanded beginning with 320 grit while using foam sanding pads. It quickly progressed to 600 grit. The mold was then washed and dried. Machine glaze was spread on the surface and hand polished using terry wipes. The molds were then waxed 6 times, again allowing an hour between every 2 coats. At this stage, both the upper and lower molds were perfectly polished and ready for use in vacuum bagging fabrication.
The plug construction portion of this project took longer to complete than necessary. In the end, 2 perfect molds were produced, but they could have been done sooner and easier with more forethought at the design stage. I was eager to get building and left some quality issues in the cross-section designs unaddressed. I knew I could compensate for it later, so I forged ahead. It's a testimony to the composite materials themselves that such fine products can be made from such humble beginnings. Take it from me, it is better to spend an extra week at the drafting table or computer than an extra month in the shop. Remember the phrase, measure twice, cut once.
Following the molding portion of this project, the student team from the University of Akron had a working knowledge of the plug concept and mold making techniques necessary for completion of a project on this scale. It was encouraging to hear the comments of the students as they brainstormed about other projects they could tackle using these skills and materials. It is our goal that this video has given you the same knowledge and confidence to tackle your molding projects, even if the design exists only in your mind. Using easily formed materials, you can follow this process step by step to construct your desired plug and the molds to make your parts. Consult either the sister video on sandwich core construction or our molding fiberglass video for instructions on lamination of finished parts.
The last 3 steps of molding involve preparing the mold for fabrication through releasing the final parts. These steps are covered in both our molding fiberglass and our sister video vacuum bagging techniques and sandwich core construction.
Remember that you can call and talk to Scott or any member of our customer service team, and we will be glad to help you with your questions and your project. We want your project to be a success. Thank you for watching.